Good morning, topology fans. I'll bet you can guess who this is, even though it's been a while since we've seen each other. Looking forward to teaching this subject because, as you know, it combines ring theory with topology, which are my two favorite mathematical subjects. So let's pray and get right into it. Father, in the name of Jesus, we welcome you to this broadcast. We thank you, Father, that you've made students so diligent and so desirous of learning more and so intelligent that they're able to handle this kind of stuff. And Father, I pray that you'll help me to handle this kind of stuff this morning, and I pray that you'll help the students to really understand it, to really get it, and to continue developing a love for it. In Jesus' name, amen. All right, let's go right in. We last time talked about prime ideals of a ring, and then there's such a thing as a prime ring. It doesn't mean that the ring itself is a prime ideal. That's not possible. A prime ideal precludes being the entire ring, but the ring being a prime ring means that zero is a prime ideal. So I want to point that out. So the definition, I guess, R is a prime ring if zero is a prime ideal. Now you remember from last time, hopefully, that what it means to be a prime ideal is that if you've got an ideal that is P is a prime ideal, means that if the product of two ideals is contained in P, then one or the other or both of the ideals must be contained in P. In this case, P is the zero ideal. So if the product of two ideals is zero, then one or the other ideal has to be the zero ideal. Now, obvious example of this would be the set of integers. A set of integers, you remember that in a commutative ring, the definition of prime ideal reduces to P is a prime ideal if whenever the product of two elements is in that prime ideal, then one or the other element is in that ideal. So in this case, in a commutative case like Z, that just says that there are no zero divisors, because if A times B is equal to zero, then either A or B is equal to zero. So a prime commutative ring is a domain. If the commutative ring has a 1, then a prime commutative ring with 1 is an integral domain. So Z is a nice example of a prime ring. And of course, the prime ideals of Z are the ideals that are generated by primes. In other words, they're all of the integral multiples of a prime element. And the only prime ideals in Z are P times Z, where P is some prime integer, and this one, the zero ideal. As it turns out, in the integers, all of those prime ideals except this one is a maximal ideal. I want to remind you what a maximal ideal is. It's the biggest one, but just a reminder so that it brings it back for future references in the Zariski topology examples. So definition: M is a maximal ideal of R if, of course, M is an ideal of R. It'd be kind of boring if that's not true. And if no other ideal properly contains M except R itself. So if I contains but is not equal to M, then I equals R. Okay, that's what it means to be a maximal ideal. Now notice that in the example of the integers, let's take the prime multiples of the integers, 7z. Okay, is there any ideal of the integers that contains 7z properly? And the answer is no, because Z is a principal ideal domain. I think we defined that last time. Principal ideal, a principal ideal ring is a ring all of whose ideals are just multiples of a single element, or they are generated by a single element. Multiples of the element itself if the ring has a 1 in it. Otherwise, we're going to talk in just a little while about what it means to generate an ideal. But all of the 7 times z is the largest ideal of z that contains 7 times z, except for z itself. So 7z is maximal, and of course that's because you can't factor 7 into a product of other integers other than 1 in itself, or the negatives of them. Don't want to get too bogged down in the precision here. If you have 14z, 14z is properly contained in 2z, and it's properly contained in 7z. So 14z is not a maximal ideal, and of course it's not a prime ideal either. In the integers, the prime ideals and the maximal ideals are the same, except for this one. And we're going to be able to see that very clearly. And of course, this is not a maximal ideal simply because it's contained in all of the ideals. But let's do some criterions for when a ring is a prime ring. So theorem, I'm not going to give a number to it because it's not really in your text. R is a maximal, R mod M is a simple ring if and only if M is a maximal ideal. Now you remember what a simple ring is. We talked about that quite a bit in Linear 2. A simple ring has no ideals except itself and the zero ideal. Of course, every ring has 2 ideals, itself and the zero ideal. But if it has no other ideals, it's called a simple ring. Example, take the n by n matrices. Well, first of all, every field. You proved this last semester in Linear 2. Every field is simple. The matrices over a field is a simple ring. The n by n matrices over a simple field, over a field. The n by n matrices over any simple ring is also a simple ring. So R mod M has no ideals other than itself and zero if and only if M is a maximal ideal. Not too difficult to prove. There are 2 things to prove. Let's go this way. Suppose R mod M is simple. Then suppose, so we're going to do this by contradiction, suppose M is not a maximal ideal. case you're wondering, we're not talking about any topology here, and this is a class in advanced topology. Where in the world are we going? And the answer is we're going to be defining a topology on the set of prime ideals of a ring. So that's where we're headed. But we have to do quite a bit of background first. So suppose that R mod M is simple, but M is not a maximal ideal. Since M is not a maximal ideal, there must be a bigger one between M and R mod M, between M and R. So then there exists some ideal I of R such that I contains M and I is not the whole ring. Okay, that's what it means to be, for M to not be maximal. Then in R mod M, the set of cosets I plus M is a non-zero ideal of R mod M. Okay, because it properly contains the zero of R mod M. Well, problem with that is R mod M is simple. And if I plus M is a non-zero ideal of R mod M and R mod M is simple, then it has to be the whole thing. So I plus M equals R mod M, so I equals R. All right, so we have now shown that M is a maximal ideal. Actually, I didn't do it by contradiction. I just showed if I have an ideal that properly contains M, then the ideal is R. Okay, now let's go the other direction. Suppose M is maximal. To show that R mod M is simple, let's say J bar be a non-zero ideal in R mod M. Okay. Well then, J bar is a set of cosets formed from J plus M, where J is some ideal of R. Not a very good triangle here. Okay, so if I have a non-zero ideal in the quotient ring, then it pulls back to an ideal in the ring that contains M, because M is the zero in the quotient ring. Okay, but now what's wrong with that? Therefore, J plus M contains and is not equal to M, because J bar is a non-zero ideal in R mod M, so J plus M has to contain M properly. Therefore, J plus M is equal to all of R, Hence, R mod M is simple. And that's the end of it. Okay, so R mod M is a simple ring if and only if M is a maximal ideal. Similarly, R mod P is a prime ring if and only if P is a prime ideal. This one's going to be of interest to us as well, since the Zariski topology has to do with prime ideals. So let's prove this. It should also be simple. No pun intended. Okay, suppose R mod P is prime, a prime ring. So if R mod P is a prime ring, to prove P is a prime ideal, now what's the definition of a prime ideal? We take everything back to the definition. The definition of a prime ideal is if I multiply two ideals together. If the product is contained in P, then one or the other is contained in P. And recall what I mean by multiplying two ideals together. It's the set of all finite sums of products of elements from the two ideals. Okay. So to prove that P is a prime ideal, suppose that I and J are a couple of ideals of R, and that their product lives in P. So Ij is contained in that ideal. Okay. Now, suppose that neither one of them are contained in P. So this is not the product of the two of them. The product of the two of them is contained in P. But suppose that neither one of them, is contained in P. All right. Then now, if neither ideal is contained in P, then I plus P times J plus P, well, that's equal to Ij, and then P times J I times P, and P squared. Well, Ij is contained in P, Pj is contained in P, Ip is contained in P, and P squared is contained in P, so this whole mess is contained in P. So now, let's project these two ideals into the quotient ring, R mod P. So I bar times J bar is equal to 0 bar in R mod P. Why? Because these are the cosets of I, these are the cosets of J, and so the product of the two, since the product of these is contained in P, P is the 0 in R mod P, so the cosets times these cosets give me something inside P, in other words, 0 bar in the quotient ring. But what do I know about R mod P? R mod P is a prime ring. So you can probably smell what's coming, but it's not going to come until I can erase this other board. So let's see how fast I can do that. It looks like my pen is a little stronger than the last one was. But we're going to get there. There we go. Okay. So, since R mod P is a prime ring, and the product of these two ideals is 0 in that prime ring, then either I bar equals 0 bar, or J bar equals 0 bar, i.e., now what's the 0 in R mod P? It's P. So I would have to be contained in P, or J is contained in P as needed. Okay, and that's the end of the proof. That's the end of this half. Sorry. A little too much enthusiasm here. Let's go the other way. Suppose that P is a prime ideal. To show that R mod P is a prime ring, suppose that the product of two ideals in R mod P is the 0 ideal. Suppose I bar J bar is equal to the 0 ideal, where I bar equals I plus M. R plus P, sorry. And J gives you the cosets. J bar gives the cosets of some ideal J plus P, where I and J are ideals of R. So in other words, in the quotient ring, we're now pulling back to R to find the ideals that gave us I bar and J bar, and we're going to call those I and J. Okay? Then since I bar J bar equals 0 bar, then I plus P times J plus P has to be contained in P. So IJ plus PJ plus IP plus P squared is contained in P. But all of these are contained in P because P is an ideal. And so IJ is contained in P. But what do we know about P? P is a prime ideal. So I is contained in P or J is contained in P. Therefore, I bar is 0 bar or J bar is 0 bar in R mod P. Thus, R mod P is a prime ring. And now we're done. Okay. Let's see. One more thing that I'd like to prove. I'd like to prove that every maximal ideal is a prime ideal. And that's going to be really easy to prove, I do believe. Find a place for my pen where it doesn't roll off. Okay. Okay, let's show that all maximal ideals are prime. Let me point something out. If we were in a commutative ring, in fact, a commutative ring with 1, you proved in linear 2 that every commutative ring with 1 has a maximal ideal, and that every simple commutative ring with 1 is actually a field. And so if I were in a commutative ring with 1, then every maximal ideal, if I take the ring mod that maximal ideal, now I have a simple commutative ring with 1, which means R mod M would be a field. And so certainly R mod M would be a prime ring because fields do not have any zero divisors. Since R mod M being a field implies that R mod M is a domain, a prime ring, in the commutative case, then every maximal ideal is prime in a trivial way for commutative rings with 1. But is it true in general? Is every maximal ideal a prime ring in general? The answer is yes, and because we've laid all this groundwork, it's actually pretty easy to prove. By the above theorems, it is enough to show that every simple ring is a prime ring. Now, why is that enough to show that? Because suppose that I have a maximal ideal, call it M, okay? Then I want to show that M is a prime ideal, okay? But in order to show that it's a prime ideal, it's enough to show that R mod M is a prime ring. Well, R mod M is a simple ring by the theorem that we did previously, so it's enough to show then that a simple ring is a prime ring. And so all we have to do is just throw away the ideal and pass to the quotient ring and deal with simple rings and prime rings rather than maximal ideals and prime ideals. So that's the game plan. And it's because of these two theorems that we can do that. It's enough to show that every simple ring is a prime ring. So recall that the definition of a simple ring has two parts. First of all, its only ideals are 0 and the whole ring. And secondly, the multiplication is not trivial. In other words, A times B can't be 0 all the time for all the A's and B's. There's just no multiplication at all. That can't be true. And we write that as R squared is not 0. Something in R times something in R cannot always give us 0. There's got to be some non-zero products in here someplace. Okay? So that's the definition of a simple ring. So let R be simple. Now, where is this forcing me to go? I have to show that R is a prime ring. What does it mean for R to be a prime ring? I'm doing this here. It means that 0 is a prime ideal. So we must show that 0, the ideal generated by 0, which is just the one element, is a prime ideal. In other words, if let's use, we'll use I and J again. If I and J are ideals of R, and IJ is the 0 ideal, then either I or J is 0. I is the 0 ideal, or J is the 0 ideal. Okay? So, suppose that I is not 0. Okay? Then we must show J equals 0. Okay, if I is not 0, then the other one's got to be 0. So we must show J is 0. If J is not 0, then since R is simple, J has to be the whole ring. Okay. Therefore, I times the whole ring is equal to 0. But what's wrong with that? What's wrong with that is that the same reasoning shows that if J is not 0, then since R is simple, J equals R. But if I is not 0, I equals R. But similarly, I equals R. So R squared equals the 0 ideal, which is a contradiction. Okay, so simple rings are prime rings, and so what that gives me is maximal ideals are prime ideals. And we're going to be defining the Zariski topology for both of those animals. So that'll have to do with one of your homework assignments. You see how I try to set you up for homework assignments? I don't want you pulling out your hair when you're doing homework problems. I'd feel very guilty if I came back to school and I saw you guys with no hair. Alrighty. Definition. Okay, well, you know how I like to, before I do a definition, how I like to sit down and talk. Where are we going? If you ask many people what mathematics is about, many people will tell you it's the subject of solving equations. And algebraic geometry, that's actually kind of the truth. Now, we know that mathematics in general is much bigger than solving equations, but in the field of algebraic geometry, you can see where all these things are starting to tie together. Algebraic topology, differential geometry, topological groups, manifolds, topological vector spaces, topological groups are all of these things are combining together. Lie groups are topological manifolds. And algebraic geometry has to do with the solving of equations. Now, it has to do with a lot of other things too. But let's take a look at the subject of solving polynomial equations and see where that leads us topologically. Definition. In your notes, this is definition 64. An algebraic variety, you may have heard the term before, in R or C is the set of zeros, and I suppose instead of saying in, I should probably say over. R or C is a set of zeros of a set of polynomials. Over R or C. Okay, so real or complex polynomials. Consider, for example, in R, consider the polynomial in two variables, y minus x squared. Now, what does the set of zeros of that polynomial look like? And of course, you've known that since you were in junior high school. It looks like this. The zeros of this polynomial look like this in the real plane. Now, if you look underneath definition 64 in your notes, because I can't really draw this picture very well, you get a beautiful rainbow picture of that same variety, but in R3. So let me say in R2, consider y minus x squared, and it looks like this, but in R3, it's a bit different. Because what happens in R3 is you're taking this graph and you're kind of projecting it forward. And that beautiful picture is in your notes. With This is only the set of zeros of one polynomial, and that's easy to graph. Even in R3, with a computer, it's easy to graph. But what if you have a set of polynomials? What if you have several, 2 or 3 polynomials? What if you have 117 polynomials? Then these varieties get very, very complicated, very difficult to graph. And if you go to Wikipedia, look up algebraic variety, you'll see pictures, immensely complicated pictures of algebraic varieties. And the more, obviously, the more polynomials you have, the more complication that you have in the graphs. But let's let R. Now, this R is not the real numbers. This R is a ring. And to be precise, it is the polynomial ring with complex coefficients and n variables. Okay? Obviously, that collection of polynomials is a ring. You can multiply polynomials and blah, blah, blah. Add them, subtract them. And this particular ring is an integral domain. It certainly has a 1 because 1 is a polynomial in these variables. 0 times this one plus 0 times this one, blah, 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 plus 0 times that, plus, oh yeah, 1. So 1 is a polynomial in this ring. And it's a domain. So R is an integral domain because R is commutative. It has a 1. And there are no non-zero zero divisors. I'll be precise about this. Non-zero zero divisors. Now, what does it mean that there are no non-zero zero divisors? What is a typical element of this ring? It's a polynomial. So if f of x1 through xn times g of x1 through xn equals the zero polynomial, then either f or g is the zero polynomial. Okay, that's what it means, that there are no zero divisors in this particular ring. So let me do a little more erasing, and we'll push this a little farther. Okay. Definition. An affine space, and we're going to call it an affine n space over, and we can use any field we like, but I'm going to put it over C. The notation is going to be a to the n, and I should make this a special kind of a. don't know, that doesn't look very special to me, is a set of n tuples over C. Okay. Now, what is an affine space? How can I picture an affine space? It's sometimes, an affine space is sometimes described as a space that is a translation of a vector space over C. It's a space that has forgotten where its origin was. So we're going to see some examples of this. Let's do an obvious example. From linear algebra, we know that the set of solutions of a homogeneous system of equations, the set of solutions to the homogeneous equations A vector x equals the zero vector. So that's a system of, say, n equations, and it doesn't matter whether there are more equations than unknowns or not, but the set of solutions to the homogeneous system is a vector space over the field. The set of solutions forms a vector space over the field. If I have two solutions, the sum of those and the difference of those is also a solution. You can multiply a solution by a scalar, you still get zero, etc. But the set of solutions to the non-homogeneous system AX equals, say, some vector B, where B is not equal to the zero vector, is not a vector space. Now, what's the relation between this, the set of solutions of this equation, the set of solutions of this equation? The answer is, if you take this vector space and you translate it by the non-zero vector, then you get something that looks very much like that vector space, except it doesn't have a zero in it. It's not a vector space. It has no zero vector. And there are other problems too. It's not closed under addition. If I take one of these solutions and add it to another one of those solutions, and I hit it by the matrix A, then A times the sum of those two is going to be B plus is going to be 2B, which is still not zero. Okay, so this is not, and it's certainly not equal to B. So this set of solutions to the non-homogeneous system is not closed under addition. However, but the difference of two solutions to AX equals B is a solution to AX equals 0. That should be obvious to you. Okay. Let's do another example. Let's do some numbers. First, Let's erase a board. So another example. Consider the real solutions to 4x minus 3y plus 6z equals 24. Okay. Now, the set of solutions to this equation is an algebraic variety. Now, because if I take the 24 to the other side, then I have the polynomial 4x minus 3y plus 6z minus 24 equals 0. And so the set of solutions of that is going to be a variety. You have a nice picture of this on the next page from the page we were just talking about before. You have a nice picture of this particular variety. It's a plane, but it doesn't go through the origin, obviously, because if it went through the origin, then this would have to be 0. But notice that, let's see, let me pick one. Notice that 15, 8, negative 6 is on, and what shall I call this thing? Let's call this thing L. Where L is the given plane. Okay. And of course, it's easy to check that 4 times 15 minus 3 times 8 plus 6 times negative 6 is equal to 60 minus 24, 36. Let's see, 60 minus 24 minus 36, which is equal to 0. So that's not on that plane. I'm one step ahead of myself here. Hang on to that 0, it's coming. But 9, 6, 1, and negative 6, negative 2, 7 are on this plane. Okay, you can call it L or not call it anything at all. But these 2 points are on that plane because 4 times 9 is 36, minus 3 times 6, which is 18, so we're down to 18, plus 6 times 1 is 24. And same thing for this point over here. But the difference which is the vector I gave you before, 15, 8, and 1 minus 7, negative 6. is on the plane through the origin, solving 4x minus 3y plus 6z equals 0. Now, probably a lot of this stuff, or maybe all of this stuff, is totally obvious to you. But what I'm trying to point out, and what the diagram on this page points out, is that we have a plane that actually slants up. It's up above the origin. And so what is it? It's a plane, so it's homeomorphic to R2. In fact, it's diffeomorphic to R2, but it's not a vector space. It's because it doesn't have a 0 in it. So an affine plane looks like a vector space, but it doesn't know where the origin is because 0 is not in it. Okay? Now, we know what an algebraic variety is, definition, and we know what an affine space is. An affine variety is an algebraic variety. In other words, it's the location of the zeros for some set of polynomials. It's an algebraic variety. That is the set of zeros for a set of polynomials that generate, and I'm going to put the word generate in quotes because I need to define it, that generate a prime ideal in the polynomial ring. Okay, so let me give you an example, and then we'll talk about generating ideals. So consider the polynomial ring in two variables over the complex numbers, and let f of xy equal, let's see, x plus y, and g of xy equal x squared minus y. It's all the negative of the polynomial that we were looking at, the variety of before. Okay, now, c of xy can be, ideals in c of xy can be generated by any number of polynomials. Okay, but consider now the ideal I in c of xy. I'm going to put the word generated in quotes again. generated by f and g. In other words, I is equal to, let's call this polynomial ring R again, okay? I is equal to anything in the polynomial ring times f plus anything in the polynomial ring times g. Okay, so I is the smallest ideal of R that contains both f and g. And we're hitting on what the word generate means here. Now, suppose that some polynomial h of xy is an element of I. How could h of xy be an element of this ideal? Well, in order for h of xy to be an element in the ideal generated by those two polynomials, it's got to be either in here or in here. In other words, it has to have f as a factor, or it has to have g as a factor. It can have both of them as a factor, but it has to have one or the other as a factor. Now, notice the reason that that's true. The reason is because both of those polynomials are irreducible. In other words, you cannot factor x plus y or x squared minus y into, oh, you know what? Let's make this x minus y. Sorry, just erase that square, just so it's simpler. You can't factor x plus y any further. It's a first degree polynomial. You can't factor x minus y further. It's a first degree polynomial. And so if h of xy is in the ideal generated by those two, it's got to have one or the other or both of them as a factor. So this whole issue of affine varieties is going to have to do with irreducible polynomials. And an irreducible polynomial is a polynomial that cannot be factored into the product of two polynomials of lesser degree. The only way that, in fact, you can't, that's it. You can't factor it into a product of two polynomials of lesser degree. Okay, because there is, now, the only exception, of course, is that a constant has degree 0, and you can factor these polynomials as some constant, non-zero constant, times a polynomial of the same degree. But taking, say, 1/2 times 2x minus 2y is not what I mean by factoring it where both of the polynomials that you factor it into the product of would have to have lesser degree. So if one of them has degree 0, the other one would have to have degree 1, and so it's not a product of two polynomials, both of which have lesser degree. And the same thing is true for this one. Irreducible polynomials, they're at the heart of this subject. Now, let's describe what I mean by generating, an ideal generated by certain elements. So let R be a ring, and let I be an ideal of the ring. We say I is generated by the element, take a lesson in spelling here. Glad you couldn't see it because I was in the way. By the element R if I is the smallest ideal containing the element R. Now, if I have a set of elements R, so I is generated by some set, say R sub I, if for all A in I, A is a sum of products of the R sub I with elements of the ring. Okay. And the way we write that is that I is equal to the ideal generated by the R sub I. We use those wedges for generated by. If there are finitely many of the R sub i's that generate the entire ideal I, we say that I is finitely generated. So if the number of R sub i's is finite, I is said to be finitely generated. Okay. Let me do a little bit of erasing. Did I want to make any other comments about this? And of course, I is the smallest ideal containing all the R sub i's. It is also thought of as the intersection of all ideals containing all the R sub i's. Okay. If R is a commutative ring with 1, then if I is equal to the ideal generated by R1 and R2, I is equal to R times R1 plus R times R2. It's very simple. And of course, R1 and R2 are in this ideal because if 1 is in the ring, then R1 times 1 is in here, R2 times 1 is in here, both of them are contained in the ideal. The problem comes if R is non-commutative. Then what does I have to look like? Well, first of all, I need all the multiples of R, all the sums of R1 with itself, all the sums of R2 with itself, and then I need these times elements of R in any order. So I need all of the R1s plus all of the R1 times R's plus R times R2 plus R2 times R, or plus maybe R times R1 times R plus R times R2 times R. So you see the problem occurs in the non-commutative rings, which is why I love non-commutative rings so much, because you get to solve more intricate problems. So next time, we're going to actually take a look. We're going to get to describing the Zariski topology, and I'm looking forward to it. I hope to see you guys very soon, but for now, you have to listen to me. So God bless you guys. Stay safe, and we'll talk to you soon.